Hello again and welcome. Today we're going to start life cycle testing the UT61E+. To do that, we'll be using this small M-Drive 17 stepper motor. At the tips of the fork are two pieces of soft rubber. We'll solder a couple of wires to the switch contacts, and we'll use our bench meter to monitor the switch contact resistance throughout the test. So this UNI-T will be the 11th meter that I've life cycle tested. So I think before we get started, let's just review some of the previous life cycle tests. It looks like it's pretty much up to speed now. Alright, so this is going to take about 60 hours again. This is why the springs aren't working anymore. I'm kind of surprised that they would have used a plastic that would break that quick. They hardly look worn at all. See that? It has almost like a chatter mark to it. You can see like here it's dark, and then it gets light, and then it gets dark. It's just a very odd pattern. And then you notice the outside ring. It's nice and smooth.
And we've actually hooked up some wires here to the off position of the unit. So when it's in the off position, we'll actually be able to measure the contact resistance here, but we've actually changed our jig over here to actually measure this. So we're using an ADC on here with a parallel resistor in there, a divider resistor, and then a parallel resistor just in case it opens, and then we can calculate the actual contact resistance. What does our contact resistance go up to, David? About 10 ohms. Anyway, we've tested it, and our nominal contact resistance is about 0.9 or something like that. So, of course, we expect that to vary a lot and change as we cycle through the automated testing. But anyway, we're going to try it with the new shim, get our automated tester, and whack it in there. So.
Meter now has about 2,000 cycles on it, just a little over. Again, these are pretty worn down, but at least they didn't crack like the Keysight meter. Hopefully this shows up, but you can see that's a definite metal shaving. And there's quite a few others you can see, like right here in the center of the screen. That's all copper. Up here Again, more shards of copper. Here's another piece right along the edge. So when I was talking with Bryman about running this switch life cycle test, it turns out they actually do a test similar to this. They sent me a few clips of their test jig in operation, and they've agreed to allow me to include those as part of this video. So I'm going to go ahead and do that. You can hear the software slowly increasing the speed of the motor, and that's because it's trying to determine how fast it needs to cycle this switch in order to complete the 50,000 cycles in the 60 hours. So I've just finished the 50,000 cycles. You can hear it clicks pretty good still. Again, the meter on the right is the one that I purchased originally, so this meter is a little over 2 years old. Let me just rotate the dial on both meters to give you an idea what the two sound like. And again, the circuit board looks pretty good. Looks like there's a little bit of buildup on it. Again, just some buildup around the tips, but all in all, they look pretty good. This is looking at the opposite side of the rotary switch. During part 4, I had asked how you wanted us to proceed with the testing. The majority of you who responded wanted to see the switch life cycle tested. So you can see I've got our stepper motor out. And I've gone ahead and I've attached a couple of wires. You can see where I've got one point right here, and the other one is tacked onto the ground plane, and that switch contact activates on the non-contact, the amps, as well as the DC and the AC volts. So we'll be taking the measurement when we're in the non-contact voltage setting. So this is the fork that I'd used last time. You can see it's just too tight for this knob, but this wider one that I had machined up is a very good fit for this. I'm not expecting this to cause any problems with this outside rubber on the knob. We'll find out. My plan is to just run the wires out like so. The contacts on this particular meter are greased. I've ran meters before that had grease on them. I really don't know if that helps the contacts last longer or not, but I can tell you that I know several people that purchased the UNI-T UT181A. That's a small current clamp meter, and what we've noticed is that the switches on those are failing, and that's with moderate use. So I would imagine that the contacts on this meter probably are not going to fare very well. But again, this will be the very first time that I've ever looked at a UNI-T product this way. So it'll be interesting to see how this all pans out. All I do is take our little wire wrap it around our two wires. Again, these wires go back to my HP bench meter. I'd rather use a piece of equipment like that to measure the resistance. We're going to use this block to take up some of the gap. You can see it's in there pretty rigid now. Again, the idea is to just get this thing lined up so there's no bind at all. Everything just fits really nice. No problem. Looks good. The software is trying to learn how much torque is required to turn the knob. That's going to rotate the knob looking for the two end points. Now it's adjusting the speed. And again, I want to be clear that one cycle in this test is rotating from off all the way to the non-contact voltage and then back to the off. So fully rotating the knob in both directions, I consider one cycle. Basically what I do is I program in how many hours I want this test to run. In this case 60 hours is what I've been running them, and we want to complete 50,000 cycles in that time. The software will continuously adjust this rotational time. So far the resistance looks good. I would say it's on par with every other meter I've looked at. Of course, we're just getting started. It's got all of 40 cycles so far. Alright, we'll just let her sit. Alright, we have a little over 2,000 cycles on the meter so far. And the contact resistance is basically constant so far. The meter has just over 9,000 cycles on it now. You can tell it's no longer clicking. So we've already destroyed the detent spring. The other thing I'm noticing is the switch is already starting to fail. It was having problems. It looks like at about 4,000 cycles. The resistance has already gone full open circuit. Unlike the Harbor Freight meter I had aborted the test, it had gone full open but it never recovered. This meter right now is basically back to normal for contact resistance, so I'm going to continue to let it run. We currently have just under 20,000 cycles on the meter. Looks like the contacts are back to normal. I really haven't seen a whole lot more noise. So we'll continue to let it run. Is that your new toy? Huh? Is that your toy? Aha! What do I got? Huh? What do I have? What's this? Ooh, ah, ooh, ooh, ooh. Ah. The meter now has just over 40,000 cycles on it. You can tell there's basically nothing left of the detent spring. It's been very quiet for a long time now. So we got about another half a day to go. So the test completed during the night. The meter now has 50,000 cycles on it. Let me just go ahead and remove our fixture from here to here. I mean, there's no resistance at all. Right here, it's catching. But again, between here and here, nothing. And from here to here, nothing. Right there. See, from here to here. Before we take this apart, let's have a look at the switch contact real quick. Again, I'm normally measuring this with my bench meter. It's fairly high. You can see it's definitely still making contact. I think before we take this all the way apart, let's go ahead and just insert the batteries. And we'll see if the meter still powers up. You can see it resets now. Let's try reading a few components. So again, this will be our 50 ohm resistor. Looks real good. Let's try it with the 10 mega ohm. See, it's not really having a problem with this. Let's just try it with continuity. Diode check. And let's go to capacitance. And again, this will be our 150 picofarad. So the meter itself appears to be functional, other than it resets now. I think that's it. Let's go ahead and have a look. Wow. Not near as bad as what I thought it was going to be. You can see the detents are slightly wore. Kind of see along the lip to get a comparison. Really not that bad though. It looks like the majority of the wear is on the cam lobes. You can see how rounded off those are. But notice this. See those two little prongs that keep this thing locked have broken. That's why there's so much slop in the switch. Having it be broken like that may have actually helped the meter survive. You can see the tips of the contacts don't look too bad. Looking at the pads of the circuit board, it looks pretty decent. I'll go ahead and pop the two clips and let's see what this looks like. Oops, right there went one of the prongs. These probably have a taper on them, that's why they're not falling out. Let's have a look at the rubber on the outside. That was one of the concerns people had. Again, this is looking at our fork. Again, we'd like to avoid any kind of a bind, so these parts fit very loose. Alright, let's start by having a look at the case. Here's the indents. You can see they have a little bit of a wear, but all in all, not too bad really. Actually, none of the plastic in this area really looks too worn. Here we're looking at the wiper contacts. You can see the tips of these are a little wore, but not too bad. However, notice the edge right here. You can see how we fractured this contact right here. We saw that with the Bryman meter as well. It's interesting that it's split along this edge. I'm not too surprised that it broke in a corner, but I wouldn't have thought there would be a lot of side loading on it. I think this is what you're going to find with the meters that use the greases. That grease is going to trap a lot of the contaminants. Kind of makes a little slurry. Let me get the Pro Clean and we'll clean this up a little bit. Just looking at some of the debris I just removed off of these contacts. Now let's have a look at them. Again, not too bad. Just a little bit of wear. I've seen them a lot worse. I've actually seen them cut through the dimples and you'll end up with a hole right through the contact. Alright, this is looking at the circuit board. Again, you can see the problem with the grease. See how it's trapped that material? A lot of that is probably conductive. It almost looks like the wiper may have damaged that via. Same right here. Here it looks like a little bit of the plating is wore away. We're seeing a little bit of copper. This is kind of an interesting wear mark here. I'm wondering if it's not an area like this that caused enough drag on the switch, and if that's not what broke the two posts. Again, there must have been some amount of drag for it to crack those two. Now, of course, I wasn't watching this thing run the entire time, so I don't know if the meter had started to make noises. Let me just wipe the contacts off real quick. You can see a little bit of buildup. Again, right along the edge of the pads. Again, all in all though, these contacts don't look half bad. Not compared to some of the meters that we've looked at. It'd be interesting to see how this would have wore if the two prongs wouldn't have broke. Of course, that minimizes how much the wipers are moving across these pads, because they're basically just free floating on the end of the knob, but still, all in all, it looks pretty good. This is looking at the software that I use to life cycle these meters. Let's just go ahead and load up the data that we have collected so far. Alright, so looking at the file names, the first one on the list is the Agilent. This is the model number U1231A. D means that it's dry contacts, so there's no grease applied. And the other D means that the meter was damaged. So the Bryman BM786, this has dry contacts as well. This was a new meter. Same thing for the Bryman BM839 and the 869S. Here at the bottom we can see the 61E Plus. This uses lubricated contacts. It was a new meter, and this is the date that we ran the meter. So we are currently looking at the normal viewing mode. We can sort these, so we'll just select sort. And the best meter is listed at the top, and that's the Fluke 17B Plus. The next in line is the Bryman BM869S, followed by the BM839, then the BM786. Next we have the 87V, and then Dave's UEI-121GW, followed by the Agilent, and then finally the UNI-T meter that we just looked at. Now, of course, if we look at the vertical axis, this is resistance in ohms, so we're reading between 0 and 1 k ohm. And then across the y-axis, this is the number of cycles. We can see a lot of these meters are quite noisy. We can take the average of these, so we can select the mean, and this is a windowed rolling average. You can see this white meter. This happens to be the free one from Harbor Freight. So we can see what's happened with that particular meter is the contacts opened up, and then I aborted the test, and that happened at about 18,000 cycles. Another way that we can present this data is to look at all of the samples added together, and that's the accumulated mode. So you could imagine if it was 1 ohm and it always read 1 ohm, what we would see is a linear line increasing 1 ohm all the way up to 50,000. So let's go ahead and select accumulated. And what we would like again is to have this number as low as possible. So the best meters out of the group are the ones that are towards the bottom here, and the worst ones are towards the top. And again, we can see the free meter from Harbor Freight is by far the worst, and it's flatlined here because again we aborted the test, and so of course there was nothing else to accumulate, so it basically goes flatline. Otherwise this probably would have gone right off the screen. So if we want, we can shut some of these off, give you some idea how this looks. Let's just look at the two Flukes and the Bryman meters. These are by far the best meters that I've looked at, and you can see these are all reading well under 50 ohms for the entire duration of the test. Now let's compare that with the UNI-T meter we just looked at, and we can see at about 5,000 cycles into the test, the contacts already started to open up. But what's happened is it's healed itself, and then again at about 7,500 cycles the meter goes open again, and then it stays under 100 ohms for quite some time, up till about maybe 2,700 cycles. It just crests over 100 ohms, and then we see over here at about 40,000 cycles it goes open again, and then it stays below 100 ohms for the remainder of the test. So let's just zoom into the vertical axis. Again, the blue is the UNI-T meter. Here's the Fluke 87V. This is the Bryman BM786. Here's the Bryman 839. Here's the Bryman 869. And way down here, this is our Fluke 17B Plus. You can see that meter was very stable over the entire duration of the test. The other thing about this meter is after the test was completed, the contacts on that meter look very good. The other way to look at the data is with this log-log graph. Essentially the y-axis and the x-axis are both in log. In the y we're looking at resistance, so this is 1 milliohm, 10 milliohms, 100 milliohms, an ohm, on up to 1,000 ohms. And then the vertical axis is the number of make-break cycles between 1 and 100,000. What we would ideally like to see is a meter that starts off at a milliohm and stays that way for the entire duration of the test. The closest meter that we have to that is the 17B Plus. So here we're comparing the UNI-T UT61E against the Fluke 17B Plus. The other way to look at the data is to plot the histograms of the two. So the vertical axis is the number of samples inside of the bin, and again the horizontal axis is in resistance. We'd expect the majority of the readings would be in these lower resistance values, and that's indeed what we're seeing. And of course, as we move to higher resistances, we can see that the data is more sparse. Let's just have a look at our UNI-T meter, and we can see that almost all the samples happen below 1.5 ohms. You can see as we zoom in a little further, you can get an idea how this thing kind of tapers off as we move to the higher resistances. Let's just take a look at 10 ohms, for example. It has this kind of an exponential curve to it. So the UNI-T meter is certainly not the worst meter that we've looked at out of the group, but it's certainly not on par with the Brymans and the 2 fluke meters that we've looked at. This knob is not made from a thermoset plastic, so what I've done is I've taken some plastic and I've made up a couple of new posts, and I've fused those 2 plastics together with a soldering iron. There's an arrow on this side of the detent spring, and that would line up with this arrow at the top. So this goes on this way. Like so. And you can see we're back in business, and you can see there's a little bit of slop in it. Of course, with those lobes being worn down the way they are, we'd expect that, but I would imagine this meter is still quite usable. Not too bad. Well, I think that's going to be it for this video. I hope you enjoyed it. If there's other tests that you'd like to see run with the UT61E Plus, just feel free to write in. The meter is still 100% functional, but again, it has been modified, so it doesn't necessarily represent a brand new meter from the factory. I would like to say that this meter has held up much better than what I was expecting it to based on the original UT61E. If this meter would have included a temperature input instead of the HFE mode, and if they would have kept the target price within $25, I would say, of the original UT61E, I think that this would be a really nice meter. It's obviously a lot more robust than the original UT61E. I don't like how they have these 2 pins in the switch, because all it would really take is somebody to grab the knob and try to push it beyond the detents, and it's going to snap those pins probably right off. But really, other than that, I think the meter has held up quite well. Well, that's all for now. Until the next video, stay safe, and we'll see you then. Later.